Welcome to Substrate Seminar. Super cool to have Hang here from Phala Network. Sorry guys, we just got a couple minutes behind. Apparently, Hang, you spilled some coffee on your camera. So we won't be seeing Hang in person, but he does exist. And in fact, if you didn't, we wouldn't be here. But he won't be able to see him.
Yeah.
So Hang, how's it going?
It's good. But just recent days, it's kind of crazy because we're just launching our main feature on Phala Network, actually on Kusama as a Kusama parachain. Yeah. So yeah, didn't got sufficient sleep in the recent days, but yeah, I hope it can go well in the upcoming weeks.
Cool. Yeah, crazy stuff. I mean, so like real quick introduction for you, Hang. So Hang, you're the co-founder of Phala Network and also the lead developer.
Yeah.
And so my understanding of Phala really is its kind of like vision and current state of where you guys are at with development is you're really building infrastructure for kind of enclaves for secure computation that's off chain and interacting with sort of that off chain world to the on chain world. And you're also a parachain on the Polkadot network. Is that correct?
Yes.
Cool. Yeah. Anything to add to that? While you maybe chat a little bit about sort of like what Phala is and what Kala is, I'm just going to share a link to your GitHub repository because I think that's the place where people will be able to understand that you've been losing a lot of sleep over the last couple days, and it will make more sense.
Yeah. All right. So yeah, actually today's talk we're going to cover two parts, but actually this is a really in-depth discussion. So I'm afraid maybe today we only have around 1 hour, so we can't cover everything. So I think I'm going to use the first half of the time talking about the XCM and the parachain architecture. At the same time, I would also like to give some introduction to all the people here about what we are doing as Phala this project, and there are some very interesting happening on our end. So before that, I think. I thought about if I should put the introduction in the beginning of this slides, but then I decided to postpone it into the second section. But a very short brief, I think, is we are a Web3 cloud. So maybe in the past we always talk about like we are the privacy layer on Polkadot, but now we think it's more. I think it's more suitable to say we are a cloud because we can offer some service very similar to the traditional cloud computing service, and that is like the serverless deployment, which is kind of like a smart contract, but we can do something more powerful. Yeah. So just a brief. So when we goes to the next section, I'm going to give more details.
Cool. Yeah, thanks. That's, I think, a great introduction so that folks that are new to Phala and what you guys do, have a better understanding. And also, I shared a couple links just now. So yeah, let's get this seminar going. For those that are completely new to seminar, we do this every 2 weeks. And my name is Sasha. I'm developer advocate at Parity Technologies. And we hang out and chat about cool things that people are building using Substrate. So I think this is an especially exciting topic for those that are interested or looking into the capabilities of connecting with relay chains and using the XCMP protocol for cross consensus message passing, etc. Hang's going to go into all of that. I'll just get off camera and leave you lead from here. Okay.
Okay. Thanks, Sarah.
Sweet.
Yeah. So let me start the slides. Yeah, so I'm very happy to be here. Got invited by Sarah. So yeah, so today we're going to talk about XCM, and I'm the co-founder and the lead developer of Phala Network. Yeah, so I think the first section we still focus on the XCMP itself, and especially the principle, how Polkadot make it possible. But before that, I think the biggest difference between Polkadot and the other blockchains, for example, Ethereum, and there are like some new blockchains like Solana and the other blockchains, is that Polkadot has the built-in interoperability capability. So it means that it is not a single blockchain, but more like a network of blockchains. So the mission of Polkadot is to connect the different blockchains together, and so I think these are all what is showing on the screen is just some very old topic like the block congestion, limitation of smart contract. But anyway, I think here we all know the big potential of Polkadot. So let's just next slide. How is it possible to make the different blockchains talk to each other? So this is a really hard problem, even if we are not in the context of blockchain world. For example, for any traditional distributed computing system, we have maybe multiple computers and they talk with each other, and the communication is always happening in the asynchronized way. So it means that whenever you send a message from one server to another server, you need to wait. And it is not, you have to wait for some time. Even it can be very fast, but still you have to wait for the remote server to reply you back. So this happens not only on a single computer, it happens on different servers. So the communication is always asynchronized. And for asynchronized process, the entire process is really hard to make sure it's executed in a correct way and is consistent. So when we are talking about communication, there are three basic characteristics we want to maintain. One is the message integrity. So it means that whenever you send a message from party A to party B, then you want to make sure the message is not integral. So it's not tampered by any third party. And if like you send multiple messages, you don't want the messages to lose some message when you send a sequence of the messages. The second thing I think is even more hard. So that is make the entire state system consistent. So what is consistent? If we are talking about a blockchain, then Bitcoin is very easy to come up with word like double spending. So this is a typical problem about consistency. So in a large distributed network, something happened on this end and something happened on the other end, and if they happen at the same time, and because of the asynchronized nature of a distributed system, the system have to agree on eventually agree on a single state to make sure some fact happened and happened in some consistent order. There's no possibility to exchange the order of two events, and after replying all the events, we get a final state, and the state is deterministic. So that is state consistency. If we cannot make sure the state is consistent, for example, you spend the same money on the two servers and they didn't agree on the same state, then you can double spend because they cannot communicate in a synchronized way. Yeah. And the third thing is data availability, and I think this one is not often talked very much, but there are examples. So if we can use like a blockchain to order all the messages, and after replay all the messages, we get a final state. Then that's all the consistency and message integrity problems are solved. But who are going to store all these events? And if that's a single blockchain, that is okay, right? A Bitcoin blockchain is now roughly 200 gigabytes, but and Ethereum is around 2 terabytes, I think. But when more and more blockchains join together as a single system, if you view them as a single system, the total amount of the data will grow rapidly. So we still have to make sure all the data can be retrieved in order to validate everything is still in the consistent state. So this is some more challenging problem in all the sharding or distributed system. Yeah. So how do two blockchain be interoperable? Right. So traditionally, there are already some running bridges between the blockchain. For example, the bridge between like Ethereum to BSC, right? And usually there are two kinds of bridges. One kind is the Oracle-based bridge. So basically, the both blockchain doesn't know what happened on the other side, but there are some oracles, and the oracles is just some program running by some people. Usually they are called validators because they need to stake some amount of the money in order to become a validator, and then they do a vote. For example, we see something happen on Bitcoin side, and they just send a transaction to Ethereum to say, hey, something was happened on the Bitcoin side, and as long as the vote is passed, they think this is the truth. But if we make the bridge between the two blockchains via this mechanism, it basically assume that the both blockchain are equally secure. Because if a blockchain is compromised, it can be compromised in multiple ways, but usually we just care about the finality, or I mean, the blockchain can be rolled back, right? So if like we connect two blockchains very similar to Ethereum, and one blockchain got rollbacked, then what will happen? In our in the Oracle model, if a blockchain with lower security was compromised, then all the all the events that was claimed happening on this side could be just nothing, because the blockchain is rolled back. So these events are not valid anymore. So it means that if we have a more secure blockchain and a less secure blockchain and bridge them together, then the security level of the higher one can be lowered down because it depends on the security of the another party, right? So this is a very big limitation of the traditional bridges. So how can we solve that? So Polkadot got its solution. And the solution isn't something we can just describe in one sentence. But let's just go through them one by one. The first is a proof-of-stake system and the grandpa finality. Grandpa itself is a very comprehensive protocol, but in short, you can see this picture. On a blockchain, on a grandpa blockchain, there are multiple stages for each block. And for the left two blocks, they are finalized. So finalized means this block are not going to be changed in the future, and they should be always considered as a canonical blockchain. And but for newer blocks, it may have some time to let all the nodes in the network to agree on, make them finalized. So the pink blocks, they just call newly finalized. So that's are the blocks just got finalized. And as you can see, on top of the last new finalized block, there are still a few chain candidates. So what is chain candidate? So basically, when we build a blockchain, we build some new block on top of some old blocks, right? And because the system is entirely distributed, so this node may not have a canonical view of the blockchain, especially for the newly created block. So sometimes they can go in this way, like they are building on the best block, but sometimes they can go in that way. So just under my cursor, right? They can build some block on not the best block. So it creates not a blockchain, but a block tree. So what Grandpa does is to make sure all the nodes in the network can agree on a finalized blockchain from the block tree. So and on the right side, there are validators. So some validators could be on the best chain, but some validators could be on maybe older chain. They call that the uncle blocks. Yeah. So after running the Grandpa consensus, we can have all the validators agree on all the finalized blocks. So we get a canonical blockchain. And I think the biggest I think the most important key point in this is that now all the blocks can be either finalized or not. So if it's finalized, it cannot be changed. And this is a very important property we're going to use in all the other designs. Yeah, so on top of Grandpa is just a consensus algorithm that can finalize a single blockchain. But how about how about connecting the different blockchains together? So here it comes the concept of parachain. So on Polkadot, there is a relay chain, the Polkadot main chain, and there are multiple parachains. And all these parachains, they don't have their own consensus mechanism, but they depend on parachain's Grandpa finality. So in this picture, you can see after the relay chain block 1, and parachain A and parachain B can build their own parachain block. And after that, the relay chain block 2, it not only finalized in the relay chain itself, but it also includes the parachain blocks into its own blockchain. But of course, it doesn't mean it just includes the content of the blockchain in the relay chain in this way, because in this way, it will make the relay chain block much larger, which doesn't scale. But instead, it puts a hash or some commitment from the parachain to the blockchain. So no matter how many parachains is added into the Polkadot relay chain, it only consumes a tiny bit of the storage in the relay chain. And in this way, as you can see, as long as the new relay chain block is finalized, all the parachain block before that relay chain block is also finalized. So if we think about a communication between two parachains, then we can extend the finality from the relay chain to the parachain. So this makes sure the state between the different parachains is in a deterministic way. So that is the very basic building block for the XCMP protocol. So if we go one step further, we just know there are Grandpa, and there is the Grandpa finality, and the parachain block can build on top of the relay chain. But how can it ensure the parachain's block can be run in a correct way? So the correctness. And the same time, whenever we are talking about a distributed protocol, beyond correctness, we also want the liveness. So these two things are guaranteed by a subsystem called availability and validity, right? So put it simple, it just makes sure the validators come from the relay chain, validates all the blocks from the parachain, but it's built in a very scalable way. So it is not like a very straight forward, let every validator to validate everything. It doesn't scale. Instead, there are some very clever design in the Polkadot protocol. Yeah, so it comes, I think, 4 concepts. One is POV blocks, proof of validity blocks, and the validator group, and availability course, and the approval process. But I don't think we are going to dig too deep into this topic. So I will just roughly go through them one by one, and then we come back to the XCMP itself. And with everything ready, then we can build the real XCMP on top of the Polkadot parachain system. And there's also a bonus called Spree. So if you're interested, you can search about that. But it will be a huge feature after the Polkadot parachain is launched. So basically, it can enable something never before in an interoperable blockchain system. All right, so let's just go through these concepts one by one. So what is availability and validity? If maybe you have heard about Polkadot are going to have up to 100 parachains. So it just means there are 100 times more blocks to process at any time, right? But a direct consequence of that is the size of the state will also be 100 times larger than a single blockchain. So of course we need to shard, so sharding the blockchain. But how to make the blockchain sharded? A very simple way is like, for example, we have 1,000 validators on the relay chain, and we have maybe 100 parachains. We can allocate each parachain 10 validators from the relay chain to some parachain, right? But if we shard the entire systems to n shards, then it will be n times risky to lose the data. Why? Because if we just assign like 10 validator to a single parachain, then if 10 validator all goes offline, then this parachain will die, right? Because only these 10 validators holds the data of the parachain. At the same time, the parachain itself must make sure it can go forward. So if there's not enough validators validating for single parachain, like on any how say that, the Byzantine based consensus, we need to have at least 1/3 of the validator to agree on something from this parachain, from a blockchain, right? So if we only have 10 validators, it means that if we have like more than 7 validator goes offline, then the parachain will be in trouble, right? So here comes the problem, that is the availability. We must make sure the data from every parachain can be stored securely, and no matter who wants to validate the data or the blocks from some parachain, they can do that. So now the problem becomes, how can we make this system sharded, but at the same time we can allow anyone to do the validation? So there's something called proof of verification, or it was called proof of validity in the past. But anyway, POV blocks. So this is a trick used extensively in Polkadot system. So if you heard about STF, the state transition function, it's basically your runtime, right? You put an old state, the new block, and do the calculation, then you got the new state. So this is how a standalone substrate blockchain work. But now we want to make everyone possible to validate all the blocks from the parachain. Of course, we don't want this validator to download everything, like the full blockchain history. That's too much. So instead, we can make some change to this equation. So basically, we only pass the external data rather than the entire state. Because when you execute a block, you don't necessarily need all the data from the old state, but just some reads to the database. It may just be maybe a few megabytes of the data instead of the full blockchain. And after the execution, we got the new state. But instead of storing all the new state, we can only store the state delta. And if we know the old state, we can always apply the delta and get the new state, right? So this basic transformation make it possible to build another kind of block. So beyond the block itself, we also attach all the data. When we execute this block, it reads the data. I mean, all the read data to this block, and this become a POV block. And with the POV block, we don't need to download the old state. So the validation can be done in a stateless way. Yeah. And then whenever we have some transactions, then we build this transaction as a block. And then we make the block and all the data, it reads by executing the block as a POV block. And then we have the POV block, we can push this block from the parachain side to the relay chain side. So here, as you can see in this diagram, the upper, the first half is the parachain, and the next half is the relay chain side. And when the POV block arrive to the candidates in the relay chain, sorry. So the POV blocks become something called the block, the parachain block candidate, and the candidates that is distributed among the relay chain validators, and then it follows some rule to validate everything is canonical, everything is correct, and it also makes sure the data, the POV block, can always be validated by anyone, right? And
so Hank, do you mind me just interrupting here, because I have a question just to kind of clarify,
sure.
And maybe those that are watching, I'm sure you guys maybe have questions. Don't be shy. Just use the question, ask a question box. So like I'm looking at this diagram and I'm thinking, okay, so what is what are the proof of validation of the proof of verification blocks? What do they look like on the side of the relay chain? And also a follow-up question to that is like, are there two different blocks being verified, or are they merged into one, which is the verification block? I'm not very clear on like the relationship between the blocks happening on the parachain side and those of the relay chain side.
Okay. Yeah, I talked too fast in this in this page. So basically, this is a process how a user created transaction got executed, included in the parachain side, and also it will be propagated to the relay chain side. And as a result, the relay chain must also validate that this block is a valid block. Right. So there are two processes. The first process is just very similar to a standalone substrate blockchain. So before the POV block, if you can see my mouse cursor.
Yeah, we can see it. Yeah.
Yeah, everything is just a standalone block, and it's it is validated exactly the same way as a standalone Substrate blockchain. But after that, it becomes the process to validate the parachain on the relay chain side. Then it
Got
must
it.
create a POV block, proof of verification block, and send it to the relay chain. So as long as they go to the relay chain, they become a new structure called parachain block candidate. So this block candidate contains not only the POV block, but also some other properties. And I'm going to talk about that a bit later. But
That makes
I think,
sense.
yeah, put it in a simple way. POV block is just the block itself plus all the data read from that block.
Got it. Cool.
Yeah. All right. So let's just continue. Yeah. And here, the biggest challenge, I think, maybe, I don't know, I didn't do some statistic, but I guess 1/3 of the Polkadot code base is dealing with the availability. So as I have already mentioned before, availability is a big problem. It must make sure anyone, if you want to validate some block, you can get the block, right? Not by downloading the entire blockchain from that parachain. So to make it scalable, so the way is to use something called erasure coding. Erasure coding, I'm not going to talk too deep, but basically it's a very commonly used algorithm in most of the distributed storage system. By distributing distributed storage, I mean something like Amazon S3 or like Google's GFS. So basically means if you store some file, your file will be duplicated and stored in a few places, but it's not duplicated in a naive way because you cannot predict which copy will be corrupted, right? So they apply the erasure coding. It's an algorithm to just make a single blob of the data to a field. So m of n, there is a m of n parameter. As long as you break a single file to n copies, but as long as you can have m copy, m of n, so as long as you can have m copy, you can recover the original file. So in this way, as you can see, in this diagram, it's very, I think this is very accurate. So whenever a POV block arrives to the Polkadot system, it will break to distribute it in all the validators, but it doesn't like this is a single block, right? It doesn't take the same size on each validator. It is M of n setup. So usually it's around 1/3. So this is very scalable, right? Because it doesn't increase the resource consumption by the number of the validators, but just sublinear. So the entire storage growth is in a sublinear way. And if some validator can join the system, some will leave. So as long as not majority of the validator leave the system altogether, and we can always randomly get m blocks, m copy of the data from these validators and recover it to the original POV block. So that's how Polkadot make the availability of the POV block data, and they call this system the availability store. Yeah, and but if we take a little bit deeper, then how we can make sure all these data are stored on the validators? Because validators can be malicious, and what if they just forget the data? but claiming they have the data, right? So there's an approval voting process. So whenever a block candidate arrive to some validator, of course, this validator will validate the POV block itself, but then they will put a signature into the block candidate and distribute it to the other validators. So as long as we can get sufficient validators signed the block candidate, that means these block candidates are validated. At the same time, they are stored by all these validators. So after that is in a state called backable candidate. And if a validator claim they have this POV block, they must keep the POV block in their storage, because if anyone requests for that data, but the validator cannot answer, that's a challenge. If they cannot answer, then the validator can be slashed. So in this way, we can make sure this validator actually store these blocks. And that is the first pass to make it even more, make it even more secure. There's the second phase, which is to involve even more validators, randomly selected from all the validators, and to both validate the block and also store the POV block in erasure coding. Yeah, after all these steps are good, then they are approved, so they can be included in the next relay chain block. So this is just the process after a parachain block is created and how it is confirmed on the relay chain. Yeah, so far, is there any question? Because after this point, we're not going to talk about all the low-level things.
I think you did a good job explaining this diagram, and yeah, from the whole journey, right? It's really about the journey of from parachain state to relay chain state. And I think for me, I don't have any questions. I guess I'm just speaking here just to make sure no one else has a question before we move on here.
Okay. Yeah. Okay.
Anyone?
It's already 40 minutes, so I think I'm going to speed
I think you can keep going, Han. You're doing a great job. Cool.
Okay, thanks. All right. So here comes the interesting part. How is it related to XCMP? So suppose we're going to send a message from a parachain to another. Then of course we need to trigger the message on inside some transaction. Just assume like in the second transaction we have a message produced, and then how it is transmitted to another blockchain. So in this process, first after the execution of the block, we know the outbound, I think it's better called outbound messages from this parachain, right? So actually it's a queue, right? You can produce a lot of messages, and these messages will just be queued in the blockchain storage, and then this storage is exposed in the POV block as well, because POV block, it contains the execution result. If you execute the POV block, you got the result of the block execution, and then you can know which messages are produced within this block, right? And that will go into part of the XCMP queue. There are two kinds of message passing. One is UMP and DMP. Another is XCMP. So UMP, DMP, they are up message passing, down message passing, meaning the parachain communicate with the relay chain. So like a parachain sends some message to the relay chain, that's up, that's the up direction, so UMP. And when the relay chain sends some message to the parachain, that's DMP. Beyond the UMP queue, of course, there are DMP queue. And XCMP means the parachain, two parachains, they can establish a channel between them and they can send message back and forth directly. But now XCMP is just implemented by something called HRMP. So it's just using UMP and DMP and the relay chain as a router to route the message between them, because the real XCMP is still in development, and in the future it will go live. So now all the XCMP we're talking about is actually HRMP, so horizontal. What is R? Routed, I guess, horizontal routed message passing, right? So when the block, when the message goes into the queue, then after it's included in the relay chain block and everything is already validated, then the relay chain knows what are all the messages produced before this block, and that will be stored in a message queue chain. And if you're interested, you can search MQC in the Polkadot code base. It's like a blockchain, but it's a chain of messages. And some message, if like we pass some message from parachain A to parachain B, then on the relay chain block, after they receive the message, they're going to put this route this message to the parachain, to the destination parachain, and that is the DMP. So it's from the relay chain to the parachain. So this is the process of how XCMP is implemented in the parachain architecture. Right. So what does XCM look like? So I put a very, very simple example. So here, like, suppose there are two blockchains. One on the left side, it is the a bridge to Ethereum. On the right side is Phala Network, and we are both the parachain. Then a very typical usage is to transfer some token, right? So from the Ethereum bridge to Phala Network, and the way is to create a message called withdraw asset. Actually, it should be called withdraw reserved assets, because there are two kinds of way to send the token, and the very basic one is it's called reserved transfer. And what happens? What happened under the hood? So basically, on every parachain, the other parachain can have their storage account on their blockchain. So when we send like one ether from the bridge to Phala, on the bridge side, it transfer the ether from some source account to the Phala account on Ethereum bridge. At the same time, it send a message called withdraw reserved assets to to Phala Network, and then when it arrives, and you can see the assets. It referred to how much you're going to send, right? And the effect means after the assets is withdrawn from the source, what we're going to do on the destination end. So on the destination end, there are two effects. The first one is by execution. So the XCM is created on the source blockchain, and it will be executed on the remote blockchain. And whenever some computation is happened on the blockchain, we need to have some transaction fee. So by execution, just use the token you are sending and exchange some part to the weight on the destination blockchain. It can make sure the instructions, like the next one is deposit reserve asset, and this one will cost some transaction fee, and that is covered by the first instruction by execution. And then, now we have some weight, and we have a XCM message carrying one ether, and then we are going to deposit this amount of the token to the destination account. So here, the destination account is an account in the destination blockchain. And of course, in the end, the user will not receive one ether because some part is already exchanged to buy the transaction fee. Yeah. And that is a very typical situation. But I would like to show you something more basic. So there is a palette called pin in Cumulus, and here I have the code of that. So let me make it larger. So just in case you don't know what is Cumulus, Cumulus is the parachain development, the parachain SDK. So whenever you want to convert a standalone Substrate blockchain into a parachain, you're going to integrate with Cumulus. And within Cumulus, there are some parachains for testing. And among them, there is a parachain, testing parachain called Rococo. It's not the Rococo relay chain, but the Rococo parachain, and it has some very basic feature to integrate to the XCMP. Yeah. So here there are some very basic concept. The first one is called the multi-asset. I think the first one is called multi-location. The second one is the multi-asset. So now we are not just talking about a single blockchain, right? We are talking about interaction between the parachains. So we need a way to locate where are the accounts and where are the palettes, right? So this is the first important definition, that is the multi-location. And actually, multi-location is very similar to Unix URL or Unix path, right? So it has two fields. One is parent, another is interior. Just put some comment here. So very typical multi-location is that, like, if I want to present refer to myself, we just use here, and here can be so here can be writing this way. It's a multi-location, and it's a multi-location, and this way. And parents is 0 because there's no parent, and interior is functions x1, and here are the definition of the junctions. Junction can be a parachain, can be some account, and it can also be some very generic things like a generic index, right? And there are also junctions which include multiple junction together. So x1 means a single junction. It can be like just a junction here. So this is here, and in other in some other presentation, you can just write it like this, right here. And what about if we are a parachain? What about the relay chain, Polkadot? So Polkadot should be the parent. So parent can be represented by a multi-location as well. So just the parent, sorry. parent 1 and interior here. So parent means how many level of the parent in this path. Like if now we are not a parachain, but we are like some child blockchain under a parachain, then it could be like this. Polkadot can be represented by two parents, right? Two level of parents. But this is not a very typical location. Another typical location is like a parachain. For example, if we are parachain 1 and our destination parachain is parachain 2, then we can represent the destination as like this. And if we make it a multi-location, it's like parents 1 and junction parachain ID 2. So this is multi-location, and basically you can have more fine-grained location. For example, an ERC20 token, it could be under another parachain, under some palette. For example, palette 30, which is an EVM palette, and then a contract. So, right, contract should be some generic, maybe account key 20 or some generic key. It can be whatever you want, right? As long as it can be interpreted, it's okay. Right. So in this way,
I'm just thinking, like, here, can you like show more explicitly? For example, if I'm trying to use this on my substrate chain, I'm using Cumulus, and I'm looking at this junction file, the multi-location file right now. How am I using this? Like, what am I looking out for, and what decisions am I making?
Got it. Yeah. I think to make some sense, we are better to look into some real example. So the real example is here. So it's a palette called pin, and the palette is very simple. It has the basic the very basic functionality is to send some message from this blockchain to the destination blockchain. And on the other hand, when the blockchain receives a ping message, it responds a PON message, right? So if we create like let's just ignore this one. It happened on finalized, but let's just ignore this one. So whenever we want to send a message, like here they have this defined object called XCM sender, right? We are going to send the XCM. And then we have two parameters. One is the destination, and another is the message itself. So the destination is, of course, a multi-location object. And here, this is simplifies the way to write it down. But basically, let me add some comment. It means one level of the parent, and then parachain. So so this is the multi-location of this palette. So when I want to send a message to another parachain, we create a multi-location like this, and then we can just post the message. Then the Cumulus as well as Polkadot can take care of all the rest things. Yeah.
Got it.
This is multi-location, and in this palette it sends some message called transact. So transact is the message, meaning we're going to invoke some function on the remote end. So here, as you can see, there are three parameters, and one is call. So call is just a regular substrate dispatchable call, and actually it's like this. It will invoke the ping function on the remote end with some sequence and some payload. and then it's encoded and put it into the transact message.
Got it.
Yeah, but here, as you can see,
Cool.
it shows unfinalized. So it means that on every block, this palette is going to send out some messages, and it's designed in the way to automate the test and actually spamming a little bit. Yeah. So
right.
yeah, it offers like a function called start. So basically, it adds a target to the destination blockchains, and at every block it sends the message. Of course, you can stop that, right? And here, and you can see this is the ping function. This function is not meant to be called by the user, but by another blockchain. It's just a very standalone function, but here the difference is that it calls ensure sibling para. So it means that this origin is not like a signed come from a signed transaction by the user, but instead it comes from another parachain. And
yeah, like we have ensure origin in most frame palettes, that use origins.
Yeah, exactly. Yeah, and it extracts the parachain ID from the origin. Yeah, so then it deposits an event called pint, right? And then it immediately reply another XCM. And it's very similar to the one we just checked, but this time it sent to the source of this ping message. So we just extract the origin, the para ID from the origin, and then we make it as the destination. Then we create another transact, and this time it's not ping but pong. Yeah, this is the reply. And if you check, there are two more things. One is the origin type. Another is required weight at most. So this is a way, just like when you send the Ethereum transaction, you specify the max amount of the gas fee. So this is similar. You specify how much weight you're going to allocate to this execution. And the origin type native, this is more in depth. So if you are interested, you can take a look at origin kind. This is a enum defined in the XCM protocol. Yeah, and here is the pong. So this is the handler function from in this palette, and this time it just deposits some event, and actually
right, and it's just there to showcase when ping is called, that ping sends a message, it gets passed over to the relay chain, and then the message that it receives is pong once that's done successfully, correct?
Yeah, yes, cool. Exactly. Yeah, and here it also distinguish if this parachain is ping takes. Yeah, so it has the sequence attached to every ping from, I mean, whenever it sends out a ping request, then it assign a sequence ID to the ping, and when they got a response, and usually, I mean, when the system is just executed correctly, we should go into this branch, because all the pong we got should come from the ping we sent, right? Mm-hmm. But in some other case, and this is possible if the runtime is not right in a correct way, then it shows unknown pong, right?
Cool.
Yeah, so this is a very, very simple example, and here we involve two things. One is multi-location for sure. Another thing is the junction in the multi-location. So it means that like we can have multiple level of the how should we call that, just the junction. It can be a parachain, can be a count ID to identify something in this level. Yeah, and it can also be very generic. For example, like if we deploy some ERC20 contract, so it can be not just a parachain, but some pallets in a parachain and some contract in this pallet. So it can be very, very accurate. Right? And this is also why on our end, Phala is very happy, because we can give all our smart contract an identity by the multi-location. Yeah.
Cool. That makes so much sense now. Like, yes, okay, I see much better, and now I'm seeing also where we're going to in your presentation, because I'm sure that you reserved a little bit of time to talk about like how you guys are using this in Phala, and
yeah.
And so right now, what I'm taking away is that we're really just looking at the XCMP implementation, which is the protocol, using XCM, but XCM is really like the unit of message, like transmission. You could say, correct?
Yes.
Yeah. So now what you've just specified is super cool from like a developer's perspective, because we're able to really target what in the module or palette that we want to be calling cross chain. Correct?
Yeah.
Is that okay? Cool.
Yes. Nice. Yeah, nice addition. Yeah, so this is the very basic part, but another basic part is the multi-assets. So multi-assets meaning to identify where the assets is. For example, if you mean dot can be the native asset of the relay chain, but it can also be located in another blockchain as a reserved token. And if you are interested in this concept, you can search about reserved transfer or reserved assets in the Polkadot wiki or the Web3 Foundation, the XCM research page. But that's a little bit out of scope in today's talk. Yeah. I also want to show one more thing about this demo. So here is the Rococo testing parachain. This is not a Rococo relay chain, and here you can see there are some pallets defined here. So there are XCMPQ, Polkadot XCM, Cumulus XCM, and DMPQ, and these are the two pallets that can make your parachain XCM aware. So if you take a look at the XCMPQ, right? This. So I think XCMPQ. Yeah, so here you can see you define the XCM executor, the channel info, and parachain system is the very basic palette in your parachain to manage all the parachain related stuff. And this one palette is the QF mentioned when we're talking about like the validity and how the message is included in a queue and execute and got relayed on the relay chain. At the same time, let me check. There's one more thing very important. I think it's called. Oh yeah, here it is. So it's called config, but actually this one is the XCM executor configuration. And this is like a rotor defined in your parachain. So it means that whenever a parachain, a message arrives the parachain, it determines if how this message will be processed. For example, assets transfer, that define if a transactor that defines whenever an assets related message arrives to the parachain, how it will handle that. And it also has some other definition. For example, barrier means when when the XCM goes into your parachain, of course, you don't want to execute everything, right? You need to make sure this XCM can be properly handled. So in the barrier, it defines a few things. For example, it can allow unpaid execution from parent. Parent means Polkadot. So if we have this in a barrier, it means that from the Polkadot side, if the console create some XCM message and signed it, then this XCM will be executed on the parachain without any transaction fee. And like this will allow top level paid execution from everything. Means that as long as this XCM is paid by the sender, they can execute whatever they want. Yeah. So that are the palettes as well as the XCM executor. Yeah. So if you're interested, you can try to run the Polkadot parachains, and there's a very nice tool called Polkadot Launch. Here we have a copy of that in our code base called Polkadot Launch. So basically, you can launch a parachain like this, launch a set. I mean, an entire system, including the relay chain and a few parachains in this way, like Polkadot. Oh, it's already within this directions. So yarn start and color depth.
Cool. Yeah, I'm sharing the link of Polkadot launch. It's definitely a great starting point for.
Yeah. So the configuration looks like in this way. You define, you define the relay chain, and you define the parachains, and you give it the parachain ID, and it will just create the entire network for you to play with. Yeah. All right, but we don't have time already. We already run out of time this time. So yeah, if you're interested, you can check it later. Sarah, do you think I can have maybe 5 minutes to go through?
Yeah, you know what? Usually we go on until 1/2 so you have enough time. We have one question, and I don't know if we should answer it now, but it's how could we query the storage through XCM, and should we create a new function as Ping does to query the storage?
Yeah, that's a nice question. This is a function I think mostly requested from the community, but now we don't have any XCM that can do this kind of things. So let me give you, let me check this. So here, this is XCM src with one mode.rs. So if you find this file, this is the definition of XCM. So it has a few operations. One is withdraw assets, reserve assets deposit, and the teleport. These are related to the assets. The second one is query response. And now it can only be used to query holding, and I'm not sure. Actually, I'm not quite sure if this can be used to query anything, but in my view, looks like it is just used to query the balance of some account. So to be honest, I don't know where this is sent, but yeah, in the response, it only give you how much you own. I mean, I guess this is targeting the storage account of the parachains. So storage account for parachain means every parachain have a virtual account on all the other parachains, and in this account, you can still receive some money, right? And you can send some XCM to control the behavior of that account. Like you can use that account to transfer the token, or you can use that account to maybe dispatch a call to the other pallets. But I guess this query is just meaning you can query the assets balance in your storage account in a remote parachain. And if you want to query any like storage, I think now it's not supported yet, but in the future, I see it's already being extensively discussed in GitHub. So you can search that, and I think in the next XCM version, I think in V2 also, I don't have a concrete memory, but in V2 also it will support query and response, so it will be very generic. So yeah, I guess at that time this can be implemented.
Cool.
Yeah, and transact means you can dispatch any call to the other blockchain. So this is the one we see in the demo. And there are also something like HRMP related commands, and it is used to establish the two-way channel between two parachains. Yeah, but now in V1, yeah, no, there's no arbitrary query.
Sweet. Thank you, the person that asked the question says.
All right. Yeah, so let me be as quick as possible in the next section. And in this section, we don't have any code to discuss because if we dig into the code, it will be too complex and too detailed. But yeah, so in this section, we are going to talk about extending XCMT to the off-chain world. So before this part, we are almost talking about the XCM between two parachains, right? But now we're going to talk about the off-chain world. And before that, I think I can give you some little bit introduction of the Web3 cloud. So at the beginning, actually, we call ourselves the privacy layer for Polkadot because we have a special technology called hardware secure enclave. So basically, it's a combination of the software and hardware. And secure enclave is a special area in your CPU, right? So actually, if you are using Intel CPU or AMD, or even like in your iPhone, there are secure enclave. So it's a special area. You can put some code into the area and then run that. But it's well isolated. It's two-way isolated. It's like a sandbox. And this sandbox means the code running in the sandbox cannot access anything outside that. But on the other hand, even if you are the administrator of the computer, you cannot access anything inside the enclave. So that's why it's called enclave, right? So we have this. So we can just use the enclave to run the smart contract, right? But because now the security is already how to say that we already delegated the security guarantee to the secure enclave hardware itself. So on the other hand, it means that we no longer need to run the smart contract on the blockchain. And this time, because we don't rely on the consensus algorithm, it can be very scalable. Like on Ethereum, no matter how many machines you have in the network, it's just a single blockchain. The TPS never increase. And if you have more machine, maybe more server, maybe the TPS can even go lower because of the complexity of the internet communication. On Polkadot, because we have the parachain design, which is a very, very clever design, we can have up to maybe 100 parachains, and at least it will be 100 times higher throughputs compared with Ethereum. And on our side, it's a little bit different because we delegate the computation to the off-chain world. We ask all these workers to run the computation rather than on the blockchain itself. And all these workers, they can run in parallel, right? So it means that if we have maybe 10 workers, we can run 10 smart contracts. And in parallel, if we have 100 workers, then it's 10 times compared with just 10 workers. So we call that linearly scalable. So we got two properties. One is it's scalable, but another property is everything running in the secure enclave is private, is privacy preserving by default, because you cannot steal any data from the enclave unless it's an authorized request. Yeah, so that's all for the background. And when we are connected as a parachain to Polkadot, so this diagram show what it looks like. So on the left side, there are 100 parachains. On the right side, this is Phala Network with maybe thousands or even 10,000 of workers. And actually, in our last testnet, we already got 3,000 workers. So we can use XCM to connect the workers via our parachain to the relay chain and the entire Polkadot ecosystem. And the way to achieve that, yeah, you may think it's very easy because we have multi-location. We can just locate each Phala secure enclave workers and a unique address with multi-location, and then we can propagate the message from the parachain to the workers, and then we are done, right? But actually, it turned out this is not a process that simple. So here is a typical diagram of what is happening on our end. So we have a substrate blockchain, and of course, if it's a parachain, it's connected to Polkadot. And then we have workers. We have maybe thousands of workers, and let's assume the first worker, the second worker run the contract 1 and contract 2. Then we need a way to bridge the substrate blockchain to the workers. And of course, if the worker wants to send something back to the Polkadot ecosystem, they need to submit some message back to our blockchain. So we call this process message and write back. And actually, we have 3 modules in our code base. One is the chain, of course, the substrate blockchain. On the right side, every worker are a program we call P runtime, and P runtime is like running on all the workers. So each worker run an instance of P runtime, and then we need a way to bridge them, right? Because P runtime itself is just like a service. It can listen to the connection, but it cannot proactively reach out to the blockchain. So we have a bridge called Ferry, and the bridge is responsible to listen to both the blockchain and the worker. So whenever a new block is created on the substrate end, it synchronizes this message to the worker, and back and forth. And here the user can have 2 ways to interact with the smart contract. One way is if they are going to send a transaction, we call that a command. The command goes into substrate first, and then it will synchronize to worker side by the bridge. And then this command can be executed on the worker side. But there's another operation called query. So if you want to get some data from the worker, you have to send a query to the worker directly. It doesn't go through the blockchain. Yeah, and here, as you can see, we must make sure everything comes from the substrate and from the outside world is correct and accurate, because the bridge itself is just a very simple program running on the miner end. And what if they what if a malicious miner wants to make some change to the bridge? Then they can maybe deliberately drop some block. Then the worker will maybe skip a few blocks. This is definitely not something we want to see, right? So we need authentication. So that is how we see Grandpa again. This is how we make it authenticated. On the relay chain, we have the Grandpa consensus, and from these blocks, the blocks are signed by the validators. So we can embed a light validation client in the TE side, the secure enclave side, to make sure whenever a block comes from the outside is the canonical finalized block. So, but in this way, we can make sure all the input from the blockchain side is safe. And actually, there's another direction. Whenever a worker wants to send something back to the blockchain, we also need some way to validate that. So it's a part of our key management, but we're going to skip that in this talk. It's very easy to imagine, there are multiple workers, multiple smart contracts, how they are going to interact with each other, and how it can interact with the other parachains. So the basic requirement is that every entity in our blockchain can send or receive some message. So we have something called a message queue. So the message queue is implemented as a palette. And I think, to be honest, it's very simple compared with the entire XCM system. But it has some basic functionalities. For example, we have all the entities defined in the palette, like workers, smart contracts, and palette, right? So if like a user or some entity, for example, gatekeeper, that's a special kind of worker, they want to send some message to this worker one, then they are going to post a message to the message queue on the substrate palette, in the substrate palette. And then this palette will dispatch the message to the worker end. And actually, all the worker can subscribe to any topic in this queue because all the blocks are replayed. And whenever a new message is announced, and all the worker can see that, and they can filter out only the message they care about. So in this way, we can allow any worker to receive any message from another party. And this not only apply to the workers, but also to all the palettes. So each palette can be a message sender or message receiver as long as they want. And
so, Hang, do the workers the way that, so I'm just curious whether you've kind of gotten here yet or not, but really like paying the workers sort of cross-chain, or is that something that you're looking into? Because that's kind of what I'm thinking. Like when I'm looking at this, I'm thinking, okay, like really it's you've got workers that are doing computations in secure enclaves. How can we kind of use this protocol to send assets to them, right?
Yes, that's a very good example. So actually, just till this slide, we haven't talked about how this is possible, but you can imagine.
Okay, yeah, sorry.
Yeah,
sorry if I'm breaking your flow, but yeah,
no problem. Yeah, but actually, this is already one of the last few slides. So suppose we have a smart contract. It can receive some assets from the outside world, for example, other parachains. Now, what will happen? On our end, we have the message queue, and the message queue is already established between the blockchain and the smart contract. And then, we can send whatever we want from the substrate end to the worker end. So if like a parachain sends some token to this smart contract one, then what they are going to do is that they are going to create a reserved assets transfer XCM message, and the destination of the message should be like parent slash parachain Phala Network slash smart contract one. Yeah, and the data of the message includes like the amount of the assets and the recipient of this asset. So next step, our parachain, our blockchain, receive this message, and then we can identify that the destination of this message is not a pallet or the blockchain itself, but a smart contract running in the off-chain world. So it is going to wrap the entire XCM in just a message defined in the message queue and make the recipient of this message the first smart contract. So in this way, when this block is executed, then our relayers see the new block and synchronize all the block carrying this XCM message to the worker end, and then the worker will filter out the message it should receive. So on the end, the XCM can be extracted from the Phala MQ, and then the smart contract can get the original message. So I think it should be better if we can make another slide talking about these details. But yeah,
no, that's really simple. No, you're doing a great job explaining it, and I'm kind of trying to ask questions that will hopefully for others watching later can like make things clearer, because it is very complex stuff. Like I was joking when I said it's simple stuff.
Yeah. And I think there's one more thing I want to mention in this picture, and maybe you can see a lot of keys in the workers. That is because all these workers are running in the secure enclaves. So they have the ability to deal with the encrypted messages. So for example, if like if in the smart contract 1, this is just something like an ERC20 token, and then we can expose this smart contract to the other blockchains, for example, Acala or Plasm, and their user can actually store some token in a privacy preserving way within our secure enclave workers. So when they are making some transaction, the transaction itself can be created from their wallet locally, right, within the browser or in their hardware wallet, something like that. And instead of just sending it out, they can make a key agreement with the worker. So here we have the ECDH key. It means it's a way just like the HTTPS communication channel, right? You can agree on some end-to-end encryption key between the two parties. End-to-end means one end is the user, another end is the smart contract within the secure enclave worker. So here, the XCM itself can be encrypted. So nobody will know who is sending how many amount of the token to another party. So in this way, we can make the system privacy preserving.
That is really cool. Yeah, I see that. Makes sense.
Yeah. So this is actually the last slide. So what we can build with these things, for example, we can build a wallet just like what I have described. We can build a wallet which is privacy preserving by default. So all the balances are hidden unless hidden to anyone else beyond the owner, right? This is something like ERC20 token contract, but we put it into a confidential smart contract workers. And we can also build like a DEX in the worker. So in this way, like all the transactions or this exchange orders are hidden from the outside. So it's like a dark pool, right? And we also have another team building on the loot box. So it's a combination of the NFT and our confidential smart contract. Now you can put an NFT into some confidential smart contract, so you don't know which NFT is. We can create loot boxes as NFT, and we put the real token into the box. So from outside, unless you open the box, you don't know what is carried in the box. So these other things can be combined. For example, you can treat the loot box on the DEX or you can send a token into a loot box, make it like just like a red pocket or something like a present for others, right? And we can also combine maybe with some bridges together. So I just want to say, like, the capability of XCM is very extendable. It's very easy to extend. So yeah, I'm really excited about how in the future the XCM ecosystem can evolve into some new to enable some entirely new kinds of use cases. Yeah. All right. So that's all my talk. Yeah. Let's see if there's any question.
Yeah, cool, Hang. Thanks so much. Super informative for me, especially that right now, I think it's maybe also helpful for those watching, like, that there's not a ton of documentation about XCM, XCMP, and the stuff that you were covering in your slides, which makes it more difficult for developers to really get their hands dirty on this, because you have to kind of like really dig into what's going on in the Cumulus workshop, for example, that you talked about, the palettes like Ping and Pong, and so it's really exciting, right? Because it is there. It's kind of in its nascent phase of like being really in the hands of developers building parachains right now. So, and you are one of them. How long have you been how long have you been building with Substrate, by the way?
I think 2 years. We started building on Polkadot on Substrate from 2019, and at that time it was still Substrate 1.0, I think. Yeah, before
Right.
Substrate 2.0.
Yeah. So you're one of those teams that have been around for a while, and I think it's super informative and valuable to hear where you guys are at right now in development, and sort of your vision and what you're doing right now for other teams that are also getting started. So yeah, if there's any questions, guys, we're still sticking around, I guess, for maybe a couple more minutes. I am currently just sharing something in the chat that I want to tell you guys about real quick. If there's any questions, please share them before we sign off. But while that's happening, I just shared a link to our developer conference program. It's happening on the 13th and 14th of October, and it's a 2-day event that covers all of Substrate development stuff, like a bunch of topics. I just invite you to click on that link, and you'll see all of the different topics and workshops that are happening. Again, it's Substrate Developers Conference, and you don't want to miss it. It's really a lot of fun and super informative. So yeah, share that in the chat. There's one question that came up. Oh yeah, you're answering it. Yeah, more about trusted execution environment.
Yeah. There's
Go
one
ahead.
more thing. So yeah, I'm still sharing my screen. So here we just launched our app front end, and here beyond the assets bridge, and I think that's the first bridge between Ethereum and Polkadot parachain. And here we have two things. One is delegate, another is mining. So here, as you can see, there are a lot of, we call that the stake pool. So we ask the miners to stake some money to mine. But my point is that here, there are a lot of workers already online. And if we check that, this is the best one. It has 100 workers. And these are all pools with around 100 workers. And we can also see they have some like APR calculated based on their mining reward. And here in the mining console, you can connect your worker into the network. This was just launched late last week. And
Cool.
yeah, as long as you have the capable CPU and motherboard, you can have a try. So it's very interesting. It's like mining in the early day, CPU mining in the Bitcoin early days.
Yeah. Fine. So wait, so just a quick recap on that. If we want to kind of get involved and get a taste for Phala Network and what you guys are building, we go on what was it? Can you share it in the chat? It's app.phala.network.
Yes, let me share it.
Yeah, cool. And basically we can contribute our CPU for in exchange for getting Phala tokens, or how does that work?
Yes,
cool.
Exactly.
Super neat. Well, Hang, thank you so much. This was really informative. Again, like just touching on this really exciting technology of sort of chain interoperability. Really great stuff in there, and I've learned a lot. And I'm hoping to share some new documentation on this stuff so that more developers can get their hands hot with this. But for those excited about it already, just rewatching this talk, I think, and connecting with folks like Hang in the Matrix channels is a great place to start.
Yeah, thank you very much, Sarah, for the hosting. I think this is a really nice opportunity to discuss the technology with the community.
For sure, yeah, and yeah, I'm really excited to see the development happening on your end. I know you're very busy, and I'm sure it's going to be super great stuff coming out.
Yeah.
Okay, well, if that's it. Oh, hey, you know what? There's 2 questions that I think we missed. Okay, Douglas is just quickly asking, will the system allow us to trade on an exchange without KYC?
That's a tough question. So my point is that well, it's easy to imagine, with such kind of privacy preserving system, and especially it's permissionless, it's really easy to build something fishy. But from our end, I think we were just focusing on providing the low-level infrastructure for everyone to build something good, but not something bad. But talking about the KYC, I think is still.
That's the kind of question I would say, hey, this is outside of the scope of this conversation. Yeah, I think anyway, what we're talking about here on Seminar, it's really like we're focusing on the technical details and really the tools that we're using to build things. Stuff like KYC kind of is this like socioeconomic layer outside of that. And but if that's all we have for questions, well, yeah, again, Substrate Seminar happens 2 weeks from now, and we have our Sub-Zero conference happening in October 13th and 14th. Sign up. There's a lot of great stuff to learn there. And with that being said, thank you all again for attending, and we'll see you in 2 weeks.
Thank you.
Bye.